All right, 4.3 day 2, when we look at number 12, if I've got this function and you want to have an increasing, decreasing conversation, we're going to have 3 steps. First, critical values are where the derivative equals 0 and undefined. Then I'm going to partition and chart. If you ask me to have a concavity conversation, it's going to be 3 steps. First, I'm going to find the critical values, but this time I'm going to talk about f double prime because we're talking about concavity. That's going to be step 1 is critical values. And then step 2 is going to be partition, and then step 3 is chart. So it should rhyme, right? So when I take the derivative, I get this. It's undefined where the denominator is equal to 0, which is nowhere in this case. And its derivative is equal to 0 where the numerator is equal to 0. So we get plus or minus 1. So then I partition using those critical values. I cut up the number line. So when I chart, there's my intervals, the 3 intervals that I've created. And I just plug in a value that lives in this interval. So for example, in here, maybe put in negative 100. So 1 minus negative 100 gets squared is going to be a negative 1. And this is going to be a big old positive number. Big positive number. So 1 minus a big positive is negative. Great thing, we're going to take crap and square it. So each time, this is always going to be positive in here in this column. So if I take a negative divided by a positive, because that's what my derivative is, this divided by this, I'm going to be getting a negative, which means f is decreasing. So first derivative negative means f is decreasing. A great point in this interval to test is 0. I plug in 0, 1 minus 0 squared is just a positive 1. So then a positive divided by a positive means that f prime is positive in this interval, so f is increasing. So we can continue in that fashion and get the whole chart and let the reader know where it's increasing and decreasing. And then this is how we tell where local min and max are. F prime changes sign from negative to positive. At x equals negative 1 means f has a local minimum. It goes down to up, so it must be a local minimum. Same thing for local maximum. Notice how well it's written out. Yours should look similar because you're thinking about how is the reader going to look through my work. Then we look at C, concavity. Here's step 1. Take my second derivative. So here's where it gets a little more interesting. So if I have this first derivative, when I take the first derivative, I do low d high minus high d low over low squared. Notice after that, the algebra is really where you make your paycheck. So there's an x squared plus 1 here and here. And now when I view this as a term minus another term. So in those 2 terms, I can pull this out of both to the front. And who's left behind? Well, this times this gives me the first term. And this times this gives me the second term. So now that I've factored out one of these, and there are 4 on the bottom, well, this 1 and this 4, one of those cancels out and leaves 3 in the bottom. And then when I simplify this, I get this, and now I have a nice fraction. And we like fractions and factors when we're setting equal to 0 or finding undefined. So where's a fraction undefined? Where the denominator is 0. That's going to happen nowhere in this case. Where's a fraction equal to 0? Well, that's where the numerator is equal to 0. So we get these 2 critical values. So there's step 1. So the big deal here was when we had a fraction, we had to factor out that common factor to make it look nice before we find our critical values. So step 2 is to partition and then chart. For step 3, our partition makes our 4 intervals because we made 3 cuts. And now, really clearly, I take all the factors of the numerator and all the factors of the denominator and use those to see what is the sign, SIGN, of f double prime. So I plug in some number in this interval. Well, maybe negative 100. Well, 2 times negative 100 would be negative for this factor. Negative 100 squared minus 3 is going to be positive for this factor in this interval. And then, since I'm squaring something and then adding 1 and cubing it, this factor is always going to be positive. So since our derivative is this divided by, this times this divided by this, our second derivative is going to be negative times positive, which is a negative, divided by a positive is negative. So since our second derivative is negative, we are concave down only in this interval. Okay, we're going to do that sort of conversation for the whole chart. Okay, again, notice up top, I put all the factors of the numerator and all the factors of the denominator up top because I'm just using that to find the sign. If you want to, you could just put your whole daggum derivative here and figure out what the sign is, your second derivative, but no. Okay, cool. All right, how could I make that question easier? If I had given you the second derivative and the first derivative, that would be much easier. Don't you agree? Okay, so then it's more reading from the first derivative, reading what are the increase and decrease for this thing. Well, let's do it one more time. So, since this function is f prime, well, since f prime is above the axis here and here and here, where f prime is positive, that's the same thing as f is increasing. So f is increasing for these x-value intervals. Then if you ask me, where is f decreasing? I say, well, where is f prime negative? And so where f prime is negative, that's where f is decreasing. So f prime is negative over here and over here. So your original function f is decreasing for these x values. And now where it gets interesting is you say, okay, well, where's the original f concave up or down? Well, what I tell you is, do you notice that f prime is decreasing on this interval? That's the same thing as saying that the change in f prime is negative. So that means that f is concave down on this interval because it's decreasing, and that's it. Similarly, we see that f prime is increasing on this interval and on this interval. So if f prime is increasing, that's the same as saying that the change in the change is positive. So I'd say that f is concave up on these x-value intervals. Cool. All right. What else we got? Show you a bunch of answers there. Same sort of dealio here. What do we got going on here? What did I do over here? So, okay, cool. That was me sketching a graph of f. So if f is equal to 0, could you sketch a graph of f from that? Well, it looks like we're increasing, but then our slopes go down to 0. So for f, I'm increasing, but my slopes go down to 0. And then, let's see, so my slope is 0 here. Then I get a small negative and then bigger negative. The most negative I am is here. So negative slope, most negative I am is here. And then I get smaller and smaller negative slopes until a 0 slope. That's what's here. And then my slopes are small positive up to a peak positive, which is this. And then they automatically flip around to negative. So positive, automatically flip around to negative. And then my slopes go to 0. So my slopes go to 0 right about here. And then my slopes go positive. So that would be a possible graph of f from that derivative, if you start at 0. Then, again, this is just more of those partition and chart type questions. So if I give you this function, this original function, if you were to take its derivative, that would be a increasing, decreasing conversation. So step 1 is critical values, step 2 is partition, and step 3 is chart. I cannot tell you enough, just because you know that step 1 is critical values, step 3 is partition, and step 2 is partition, step 3 is chart, just because you know that doesn't mean you're ready to go. You must do the thing. You must take a function on your own, take its derivative, partition and chart. You must take a function that you have not done before on your own, take the derivative, and partition and chart, yes? You can do this with a friend. You can do this by looking for more examples online, whatever you need to do. Or you can come in and see me any black day. But that's it for those examples, because those are all polynomials. Those should be pretty good. Let me just step over to this one, which is a little uglier. So for this one on 43, if you're going to take this derivative, we do first derivative second plus second derivative of first. It gives you this ugly thing right here, right? But then I want to find critical values, and I've got two terms, but I know that I like fractions and factors when I'm finding critical values. So by using a well-chosen one, I can now get it into a fraction, which I like much better when I'm finding critical values. So it simplifies to this. So there's the big thing. When I took this derivative, I had two terms. I had to use a well-chosen one to change it into a fraction. Okay? Notice that that happened because I had an x times the square root sort of a function. So an x times a something to the 1/2, this sort of a thing, from experience, will always be a time where I have to create a fraction. This one's going to be the same sort of deal, yeah? Okay. So 47, here it's another one of those trig things where you have to really just think about what does the unit circle look like. So when we took our derivative, we got this. We were able to factor out a sign, so it looks like this. Well, where's that equal to 0? Well, when sine is equal to 0 or cosine is -1, well, sine is y, so it's 0 here and here at those three values. Cosine is x on the unit circle, so it's -1 only here between 0 and 2 pi. So those are our critical values. But notice they partition only the interval from 0 to 2 pi, including both, because that's what they said. So that's why it turns out to be what it is. And then inside here, you're just looking for what are the SIGNs, the sign of these things. So let's just go through it. So between 0 and pi, that means I'm up here. So do you agree that y is always positive up here? So that means that -2 times a y value is going to be negative up here because sine is y. Here, if we're up here, we're going to have 1 plus a cosine value. Well, my cosine values are 1, 0, and then -1. So the biggest they ever are is 1 and -1. So if I take a -1 and add it to 1, I'm always going to have a positive value in here because you're never going to get bigger than a 1. So this times this gives us a negative, and that's why we're decreasing. So that's the sort of conversation that we have to analyze that. We can also see it because I drew it down here. Okay. So cool. Let me see what this is.
Excuse the quick interruption. House 4 field trip students.
Fun field trips. So have fun on the field trip, and I'll see you soon. Peace out. Is that about it? Yeah. Yeah. Peace out, Girl Scout.